All right, so the last talk of the day, we're very happy to have Andy Strominger tell us about quantum gravity on the celestial sphere.
And 5:20?
5:30 is fine.
Okay.
When people start dropping.
Okay, first of all, I have to apologize for spoiling the party and giving a PowerPoint presentation. But anyway, it worked better this way. Okay, so it's a pleasure to be here. This is a really fun conference. So the basic idea I'm going to talk about, which, do I have a pointer here? There. Which there's been a small group of people working on for a couple of years, is that we can take the S matrix in Minkowski space and rewrite it as a boundary on the boundary, the celestial sphere, as a correlator where we just replace every incoming particle, label it by the point or the angle at which it comes in and out of, and then these will have various other quantum numbers labeling, for example, their charge or their energy, which isn't encoded in the angle. And since the S matrix is Lorentz invariant, which is SL2C, the SL2C Lorentz group acts on the celestial sphere at infinity like the global 2D conformal group. And so this object on the right bears some resemblance to the correlator in a two-dimensional conformal field theory. Now, what gets even better, so we are familiar with the fact that in many two-dimensional examples in two-dimensional physics, that once you get the global conformal group, there's a theorem that's true in a broad variety of circumstances, you automatically get an enhancement to the infinite dimensional local conformal group. I guess there's a theorem by Zemlyachkov and Polchinski of that in two-dimensional conformal field theory. And what's interesting is that not in quantum field theory, but in quantum gravity, that also happens here. And that was shown using a soft theorem, or proving a new soft theorem and then translating into that language, so that this thing not only enjoys global 2D conformal symmetry, but the local 2D conformal symmetry. Now, there are several kind of intertwined approaches. And so we can call this, I'm going to call this object a celestial conformal field theory, but you should think of usually adjectives limit the meaning of a word, refine it, but a celestial conformal field theory is not necessarily a conformal field theory, just like a non-local conformal field theory or a non-unitary conformal field theory wouldn't ordinarily be considered a conformal field theory. So a celestial conformal field theory shares some, but not all, properties of ordinary conformal field theories. Now, there's several intertwined approaches to the set of ideas I'm going to talk about. There's a long program that began with Bondi, Metzner, Sachs in the 60s of understanding the asymptotic symmetries of spacetimes in asymptotically flat spacetimes in four-dimensional general relativity, what kind of boundary conditions you impose. Bondi, Metzner, Sachs missed quite a lot There's been new things discovered about it in the last 10 years, but we're far from, though there's some very interesting things we definitely understand, we're far from a complete understanding of that. This is tied again into, this is another approach is through Fineman diagrams and soft theorems. Again, we've understood some things about soft theorems since Bloch and Nordzig or Gell-Mann and Lowe or Weinberg more than a half a century ago, but there's still new soft theorems being discovered, and we don't quite know how to understand all the soft theorems. Another approach pioneered by de Boer and Solidukin was to sort of bootstrap the wonderful things we've learned about ADS-CFT by writing Minkowski space as a compactification to ADS. But mostly what I'm going to talk about here is this celestial CFT in and of itself. Now, I want to emphasize that unlike in most discussions of ADS-CFT, though notably not the ones we've heard today, I'm not making any microphysical assumptions. In other words, I'm not assuming, even though this is a string theory conference, I'm not assuming string theory. Everything I'm going to talk about applies to the real world. And the celestial CFT that I talk about, as far as we understand them now, are simply defined by whatever you get by transforming the S matrix into this form. Now, it would be, and I'm belaboring this because it's sometimes a point of some confusion, it would be an amazing thing, a major breakthrough, if somebody gave, it's like a holographic duality where we have one side but not the other side. It would be an amazing thing if somebody gave an intrinsic definition of a celestial CFT. So you could do calculations on one side and then on the other side and then compare them. And that might be possible. It doesn't seem ludicrous. But what we certainly shouldn't expect to be able to do would be to find the celestial CFT that describes the real world, because that is tantamount to completely, this is a talk about things that pertain to the real world, but finding the celestial CFT that describes the real world would be equivalent to knowing all the laws of physics, and I don't think we're going to get there soon. What? Good point, good point. But even in the approximation in which we live in flat space. Yeah. But that's a good point. Okay, so so why is this interesting? Well, first of all, it's just a new way of reformulating the data of quantum gravity and quantum field theory. And some things that are some important constraints, some important symmetry constraints that are not manifest in the ordinary approach are manifest in this approach, but there are other things that are manifest in the ordinary approach that are not manifest in this approach. And we'll see, in fact, a good example of that is just space-time translation invariance becomes a very highly non-trivial constraint in celestial conformal field theory. Now, somebody could correct me if I'm wrong, but I don't think, we have this beautiful story in ADS-CFT. I don't think anybody believes that holography only exists in ADS-CFT. There should be some more general formulations of it, and we should try to find, and its nature may change. We don't know which features of ADS-CFT are going to carry on to our more general conception of holography and which aren't. And so this, what is be proposing here, of course, can be thought of as a kind of holography. That is, we have a bulk space-time, and it's equivalent to a bulk space-time with gravity, which is equivalent to now a Euclidean celestial conformal field theory without gravity on a sphere. Now, also, we've been discovering recently that there are a lot more symmetries in nature than we previously appreciated, and these constrain the S matrix. And there's some simple problems you'd like to understand what their implications are. For example, the most general for Graviton amplitude. I'll say a few words about that at the end. These symmetries also constrain how black holes can form and evaporate, and may therefore be relevant to the information paradox. It's a new window on the enigmatic IR-UV connection. There seems to be that the IR physics and UV physics don't really seem to be as separate as Wilson taught us. And this is a new way of thinking about it because we throw out energy altogether and replace it by scaling dimension. And just in our adventures, we've right, okay. We found some new things. Okay, so let me start though by saying a few words about what the relationship is to ADS3 CFT2 of this kind of holography. And this was really pointed out in a prescient paper by De Boer and Solodukhin. And this paper is almost 20 years ago now. And what they said is, let's just take Minkowski space and let's do this hyperbolic slicing of Minkowski space. And here we have Euclidean ADS3, better known as H3. And here we have three-dimensional de Sitter space. And here, this sphere here, I would call the future celestial sphere. The intersection, we have to choose an origin to make this slicing. In the intersection of the future light cone of the origin, we can think of as the future celestial sphere, and the past light cone as the past celestial sphere. And what De Boer and Solodukhin said was, okay, here's an ADS3. I know what to do when I see an ADS3. I go to the boundary. There's a two-sphere. That two-sphere is the celestial sphere. And there should be some kind of infinite dimensional conformal group acting on there. And now they said, let's just think of this as kind of a non-compact. You can formally write Minkowski space as a kind of non-compact compactification down to ADS3. And if you compactify on a non-compact extra dimension, instead of having a discrete set of modes, you have a continuum of modes. But you're free to rewrite things in that way. And they said, let's rewrite this in this way, think of a theory on ADS3. So what? We've got a continuum of modes. We should still have a conformal group. And they had two conformal groups, one on the past and one in the future. And they thought that the holographic picture would somehow give you a relationship between something down in the past and something in the future. But actually what we've learned more recently is that the soft theorems and so on, I won't review this theory, but the conformal groups, there isn't a separate conformal action here and one here. They're locked together. And so we can think of the whole thing, the conformal structure on here and the conformal structure on here is identified. So we end up with just one sphere. So the whole S matrix is just a correlation on one sphere, which is a much nicer and simpler object. okay, a few years went by, and Barnick and Troussart went back and re-looked at what BMS did, and they said, wait, maybe there should also be some more transformations, the so-called superrotations, which were in fact exactly the things that de Boer and Suladukin were talking about. And then we used a soft theorem to actually prove that this conformal symmetry is a symmetry of the full quantum gravity S matrix. And there, in fact, is a direct relationship of the type that de Boer and Suladukin envisioned. That is, if you take a vector field Y, which generates an infinitesimal conformal transformation, you take its Klein-Gordon inner product over one of these slices with the linearized field modes, you get a linearized field mode of the metric. So, sorry, the subleading linearized field mode of the metric, which is known in ADS to be the two-dimensional stress tensor. You get an operator. That operator can be thought of as the stress tensor of the celestial CFT. And you can explicitly show, using the subleading soft theorem, that I've made a rather detailed story rather short here, but the basic thing is you can show that the subleading soft theorem implies that this particular mode of the graviton field obeys the Ward identities of a two-dimensional stress tensor. Okay, so we've got some kind of CFT living on this sphere, and we want to understand what are the properties of a celestial CFT. So there's some things that are similar, and some things that are different, and similarly, four-dimensional flat space holography of the type I'm describing here has some things which are just like ADS, and well, for example, de Boer and Suladukin got it from ADS, but there isn't the canonical identification. For example, there isn't the canonical identification of states in the bulk with states in the boundary, at least not in the simple way that it occurs in the ADS CFT that we're more familiar with. Okay, so let's do a comparison here. So there are two celestial conformal field theories with usual conformal field theories. In both cases, there's two Virasoro actions. In usual CFT, it's interesting to think about current algebras. In celestial conformal field theory, in fact, every time you also have current algebras which live in the boundary celestial sphere, and indeed, whenever you have a gauge group G in the bulk, you get a current algebra. The soft theorem associated with that gauge symmetry implies a current algebra on the boundary, a G-valued current algebra. In usual, and I'm going to talk about this particular line a little more because we've recently made some progress on this. In a usual conformal field theory, there's a lot of discussion of OPE, the OPE expansion. A lot has been learned by analyzing that. And in space-time theories, there's been a lot of discussion of the structure of collinear singularities when you have jets coming out in the same direction, and these are, of course, going to the same point on the celestial sphere. So in fact, these concepts are dual to one another, and we can relate them in a nice way. Now, in ordinary CFT, we have a discrete set of primary operators in highest weight representations. Here, we have continuous, it's related to already Devore and Solodukin saw this because it's a non-compact compactification. We get continuous, sort of like in Liouville theory, where you have a continuous parameter, which are typically, and the highest weight is usually complex. So that's different. There's some notion of locality in usual CFT. There's some notion of locality, depending on who you ask exactly what locality is. If locality is that you take operators around each other, you get back to where you started from, that kind of locality is okay. But there are various kinds of singularities, which are sort of like bulk point singularities that can occur for separated values of operators. Here we have unitarity of the four-dimensional S matrix. I think that's related to some kind of sewing operation, S dagger S equals 1, in the usual CFT language. There's space-time crossing, which looks something like it looks something in usual CFT like associativity of the operator product expansion. This hasn't been made precise. Now, what's really different about these is that in a usual conformal field theory, you have, just typically the only symmetry would be the infinite dimensional conformal group. But here we have a lot more infinite dimensional symmetries associated with the other soft theorems. Like, for example, just ordinary translation invariance gives a whole new infinity of symmetries. And you wouldn't think there was room for more symmetries in conformal field theories. You would think that the constraints implied by infinitely more symmetries would just annihilate all the correlation functions. But in fact, that's not true. And we know it can't be true because we have examples of these things. And turning it around, these constraints, as we'll see, turn out to be very powerful in determining things like OPEs. And okay, let me go on. So I would like to give you a sort of master picture of what a celestial conformal field theory is and how we should think about it. I don't know how to do that. So instead, I'm just going to, there's a lot of tantalizing tidbits and interesting things that we found and some things that are starting to fall together. And I'm just going to try to describe some of those. Okay. So let me now give some more details of how we construct these amplitudes. So suppose we start with some amplitude in momentum space, labeled by momenta P1 through Pn. To get the celestial amplitude, you simply do a Mellin transform over the frequencies in here of the n particles, weighted by their h1 plus h1 bar. So this is for a spin 1 for a spin 1 field. So you do a Mellin transform of this amplitude, and then you've integrated out the overall magnitude of P, but you still have this ratio left, this complex ratio. And that complex ratio is just the point on the celestial sphere to which the particle is headed. And so you end up with an amplitude now where the operators are labeled by their dimensions lambda instead of their energies omega. And it's not completely obvious, but this thing now transforms like a collection of primaries of weights h and a correlation of a collection of primaries of weight h and h bar under the conformal group. Now, this is for massless particles. You can also do this for massive particles, a little more complicated. Massive particles, the momentum lies on the hyperbola, which of course is ADS3, Euclidean ADS3. So we get the point z by convoluting with a bulk to boundary propagator on that hyperbola, and then we get similarly, so this works for massive as well as massless particles. Now, yeah.
Connection of this to CHY construction of amplitudes?
Well, yes, certainly there are many connections, but yeah, I think there are useful connections. And I mean, in the amplitudes program, people like to use the spinors and there are different formulations of scattering amplitudes. And in many different variables. And
What's the analogy could be
a sphere?
yeah, sphere and
Oh, you mean the CHI world, the fact that there's a sphere?
yes.
Yes, there certainly is, but we don't understand it. And in fact, we're going to see, I'll comment on that a little bit later on, but many of you may have noticed that we're talking about describing the S matrix as correlation functions on the sphere, and there's a few people in the room old enough to remember that there's something called string theory where we computed the S matrix by inserting operators on a sphere, and these things in fact become the same, and in that story, at high energies, you have the Gross-Mendez saddle points, which are the same as the leading solution in the CHY string, and Stieberger and Taylor showed that at high dimension, this also becomes the same thing. So these are all related in some way, but it's all still, there's clearly something there, but I can't tell you. Yeah.
It's just a basic question, but if this is a CFP correlator or something like that, where all the singularities, are all the singularities determined by OP? Because in the amplitudes we have like 3 particle singularities, right? Whereas in a CFP I would only expect like when CI goes to CJ, but in which sense like a 3 particle pole shows up in this correlator.
Excellent. That is among my list of final questions. Okay. Now, one thing also that's different about this, usually in an ordinary conformal field theory, finding the dimension of all the operators is a really hard problem. Here, we start out knowing that. That's the starting point. So for example, if we're considering a theory with, I think the thing I like to think about the most is the simplest example, is let's imagine a theory where the only stable particle is the graviton. We don't care about unstable particles in this story because they don't reach infinity. They don't get out to the celestial sphere. The only stable particle is the graviton, and then we just have this, one conformal primary operator, one continuum of conformal primary operators. So there's one continuum of conformal primary operators for every for every stable particle. So that's something we're given in the beginning.
So, if you wanted to also preserve some kind of OPE structure, then you would want to be able to merge two things. So, you would have to have multi-graviton operators too, right?
Multi-graviton. Oh, yeah. You mean just two gravitons normal order.
Gravitons, but smeared in some way against some wave function on the sphere to make a primary.
Well,
You could certainly define such things, and they would transform as primaries.
well, I think if they're smeared, they're no longer primaries, right? If you smear them on the sphere.
No, you can find, if you smear them against a conformal three-point function, you can make a primary, something that transforms like primaries. But you need these objects if you want to decompose a four-point function into blocks.
Are you talking about shadows?
Yeah.
Smearing as in shadows?
Yeah.
Yeah. Well, okay, let me just say, I don't think I have a complete answer to your question. I think it's also on my list, partially on my list of questions at the end. But, and I am going to specifically talk about OPEs, but there's an interesting statement here. Okay, so Pastersky and Shao showed that if we take all these weights, for example, if we take all these weights, then these wave functions, the conformal primary wave functions, are a complete basis of form a complete basis for normalizable wave packets. Now, that's a correct statement, but not necessarily the one we want, because, for example, if you have a wave packet that falls off like 1 over omega to the 3/4, it will be normalizable. But if you act on it with the Hamiltonian or a translation, that'll put in another factor of omega, and it won't be normalizable anymore. So what values of lambda we're supposed to be including? But actually what I wanted to say there is the range of lambda for completeness. So for a massless field, lambda runs over R, and let me ignore subtleties at lambda equals 0. Lambda runs over R, but for a massive field, which this actually also applies for, the negative lambdas are the shadows of the positive lambdas and are not. Did I get that right, Chuang? Yeah, they're the shadows of the positive lambdas, and lambda is only over positive real numbers. So there's a lot of interesting subtleties in there.
Quick question, Andy.
Yeah.
Going back to the Mellin transform, there are some choices in defining the z's and things like that. So are there interesting symmetries that relate different choices in how you...
Well, the z's, of course, the z is a coordinate on the celestial sphere. And so,
in a very specific way here, are the momenta, which presumably is a convention.
right, but the other choices would be related by a conformal transformation to this choice. Yeah. And the covariance of everything under conformal transformations means that this doesn't create a problem for us. Okay, so these amplitudes have been computed in a number of examples. For scalars, all the endpoint functions. Now, one of the interesting things that wasn't so noticed so much of the true level endpoint functions in Yang-Mills theory is that they're actually marginally convergent. The integral over omega is just marginally convergent in the UV, and there's a natural way to define it. But in Einstein gravity, they're all, if you have them, if they're of this form, then in fact you can choose H so that they converge, but if they're of that form, it's infinite, because we don't get a convergence of the omega integrals to make the Mellon transforms. So the Mellon transform of tree-level Einstein gravity, they don't exist. However, they do for string theory, and they've been computed by Stieberger and Taylor. So the Mellon transforms, in all the examples we know, they only exist for theories with good UV completions. And in fact, I would say they exist in string theory, of course, and have been computed also for gauge bosons. And I would view the string theory calculation as the definition of the end, how to deal with the marginal divergence for the Yang-Mills amplitude. So there's, in some sense, good UV properties are already baked in when you assume the existence of the Mellon transform, of the conformal, of the celestial conformal field theory. And so a conjecture here, the main evidence for which is that I don't know of any counterexamples, is that a quantum perturbation expansion of a classical field theory exists if and only if the conformal basis amplitudes exist. Now, I just want to say, I think this is the only slide or blackboard on string theory in this string theory conference. And, but there are beautiful connections to string theory emerging. Stieberger and Taylor looked at this. Alpha prime appears only as an overall normalization factor because lambda is dimensionless, so you can't have an alpha prime in there. And in fact, we could have eliminated this altogether by renormalizing the vertex operators. And stringy effects appear in the expansion in the scattering angle, and which turns out to be the scattering angle, U over S or T over S, whatever you want to call it, is the same thing as the standard invariant cross ratio in 2D conformal field theory, Z12, Z34 over Z13, Z24. Now, they moreover showed that when lambda k goes to infinity, the string world sheet becomes pinned to the celestial sphere. And this is what I was, my answer to Zvi's question. So there is some kind of relationship between the string world sheet and the celestial sphere, as we might have hoped. And what you can't see here is that I wrote strings without strings. So somehow one has a feeling in this subject that a lot of the features of fundamental string theory are already implied just by the symmetries of quantum gravity. And I think something that many people are working towards from many different points of view in our community is that there's something inevitable about the string amplitudes, and maybe someday we'll be able to show that that just theoretical considerations mandate them. Yeah.
How does this picture change if you consider, say, a compactification to a higher dimensional Minkowski space? Then you don't have this nice lineup.
Yeah, very good question. Having spent most of my life exiled from 4 dimensions, I've been very happy to think about the 4-dimensional problem, and there are maybe a dozen papers on on the higher dimensional version. There certainly are soft theorems in higher dimensions. And it is clear that there must be a conformal field theory. Conformal field theories, of course, it's clear it must be a conformal field theory in higher dimensions, just because in gravity there is no canonical way to push the sphere out to infinity. There's no way to say that I'm pushing the sphere out to infinity at the same rate at every angle. And because there's no canonical way to do that, the only kind of object which can sensibly live on the celestial sphere is a conformal field theory. So we have to have some kind of conformal field theory, but I don't know too much about it.
In that case, secondly, some connection to a world sheet is more mysterious.
Right. So that you wouldn't see the connection to the world sheet there, at least not that anyway I would know of. Okay, so this is a result which seems at once both, I vacillate between thinking it's deep and thinking it's trivial. So we can talk about conformally soft operators, where one of the weights becomes 0. Now, a conformally soft operator is not energetically soft. It involves an integral over all energies. But nevertheless, it's been shown that if you take, you make one of these lambda to 0, which would, depending on the spin, can give you dimensions like this, then you get conformal soft theorems. Actually, we've only shown this in gauge. We showed it in gravity too, and well, once you write that, it's clear that these operators have to obey some special identities. But the picture of why ordinary soft theorems are true is you have some big soft wave going through some interaction that's confined to some region. It can't see the details of the interaction. The only thing it can interact with are the long lines of particles coming in and out of the interaction region. And so there's some special universal properties that have to behave. But the conformal primary wave functions involve arbitrary high energies, so in principle they can probe the middle of things, and so it's intuitively less obvious why these theorems should be true, but nevertheless they are true. And so one example is the current in gauge theory, which obeys a theorem, a word identity like this. There's the celestial stress tensor, which we talked about earlier. But then there's an even weirder object, which is not like anything we've encountered in ordinary conformal field theory. Yeah.
Sir, can I go back to your conjecture on the previous slide?
Yeah.
So one thing that came to my mind about this kind of UV so I guess that your conjecture is kind of saying that conformal basis is a test for whether some scattering amplitudes amidst a UV completion, or whether its UV behavior can be regulated by string theory or whatever. But
Yeah.
the first thing that would come to my mind is, say, let's consider a scalar theory, and I add d phi to the 4 to the Lagrangian.
Right.
And d phi to the 4, it's famous because with one sign it emits a UV completion, but with the opposite sign it's known to violate unitarity. It's hard for me to imagine that just by changing the sign, one amplitude is finite in the conformal basis, but the other sign is not.
I think the family is not saying that there will be a UV completion. It's just saying whether the amplitude as given admits a quantum perturbation expansion. And the example you mentioned does not admit it for anything.
Oh, you were talking about a non-perturbative you're saying it doesn't exist in perturbation theory for either sign, right?
I thought
If I could report this UV divergence. I mean, you were talking about UV divergences, right?
Yeah.
That theory doesn't have a perturbative expansion.
so it's not so much about the UV completion.
Well, somebody could easily come up with a counterexample. And I'd be, yeah. But I think the point which is whether or not this conjecture is right or some refinement of it is right, I think it's interesting that good UV behavior, and we're going to see this more later, is baked into this story. Okay. All right. So these guys, so there's an operator, a graviton field operator of dimension 3/2 minus a half. And you can construct from that an operator PZ called the supertranslation operator. And the leading soft graviton theorem implies this unusual looking relationship. So there's the holomorphic 1 over z minus w on the celestial sphere, but instead of mapping the operator to itself, it shifts the dimensions upwards. And the reason why it shifts the dimensions upwards is kind of obvious if we go back to here. If we act on this with, say, a time translation, we put another factor of omega in, and that's equivalent to shifting h. So, so now we have a word identity in which we're shifting the dimension of the operator. And similar thing happens in Lowe's subleading soft theorem for QED. Actually, it shifts the dimension in the other direction. It makes it more negative. Now, you could never have anything like this in ordinary conformal field theories because operators aren't paired up. It's half-integer spaced dimensions. But here we have a continuum, so it makes perfect sense to talk about this. And so,
I'm confused about the I thought the continuum was in the imaginary direction.
the continuum was in the imaginary direction.
Is it just about
Okay. Yeah. So this is related to response to another question. So what Pastersky and Shao showed is that if we allow all these weights, that gives us a complete set of normalizable wave packets. But that basis is not closed under the action of translations. So we need to consider more operators than that. I mean, certainly in this story, we want to have everything. Ultimately, what we're doing here is trying to make everything into a representation of BMS rather than just a representation of SL2C. So, okay. So let's take now, so I'm going to show here, I'm going to talk now about the OPE between two positive helicity gluons at Z1 and Z2 with weights H1 and H2. And that, by global color symmetry, has to have this form, and the leading OPE has to, just matching up the dimensions, has to have this form, but then we have a arbitrary function of the weights H1 and H2. But now if we translate both sides of this, you see we're going to get an h1 plus a half here, and so on, and we're going to get, so we'll get 3 terms, which we'll have to add up to 0, and we find that whatever this coefficient is, it has to obey this recursion relation. Okay, now there's something which takes more time to work out, is that the subleading soft gluon symmetry gives us a second recursion relation, which now involves the conformal weights of the operators, and it's this relationship here. So now if you look up on Mathematica or Gradstein and Rizhik or whatever, these are precisely the 2 recursion relations which have a unique solution, which is assuming some behavior at large h, some fall off at large h, which have, whose unique solution is the beta function, which is this ratio of products of gamma functions. Now it so happens that Fan, Fotopoulos, and Taylor had already calculated this a much longer way by directly doing a Mellin transform of the collinear singularities. Yes, Juan.
I remember a long time ago, Greg Moore had some vertex operators in string theory. He was also deriving the Venetian amplitude from...
He was driving what?
The Venetian amplitude from thinking about some symmetries of string theory. And I think it was... Well, superficially, some words sound a little similar, so I was wondering.
I'd like to look at that.
Yeah. Okay, so this, we just reproduced what Fan, Fotopoulos, and Taylor did, but in fact, in a paper last fall with Monica Payet-Honoraclario and LSUN, we showed that all the leading OPE coefficients are determined by, you have to use the leading, subleading, and in gravity, the subleading soft theorem. And these things completely fix all the leading OPE coefficients. And we also then did the transform of the collinear singularities to verify that everything matched, but there are pretty complicated formulas there. And one interesting feature of this is that the subleading soft theorem is not completely universal. It can be corrected by a short finite list of operators. There's like 3 or 4 operators for the subleading soft theorem, depends on your field content, and also for the subleading. Now, in a pure gauge theory, there is no operator which can correct the Lowe's subleading soft theorem. But when you couple gravity, it turns out that it's corrected by the coupling from the metric, the cubic coupling between the metric and the 2 gluons. And so there's a correction to the subleading soft symmetry and the subleading soft photon theorem. And that correction has the property that it turns a gluon into a graviton and vice versa. And so therefore, all of the mixed OPEs between gravitons and gluons had some severe consistency constraints on them coming from this subleading soft theorem, which mixes up gluons and gravitons. And this is clearly related in a way which nobody's really been able to make precise. Stieberger and Taylor made some comments on it recently to the double copy story. Is here we have these operator products of gluons making gravitons. Okay, now we only analyze the tree-level Einstein-Yang-Mills, but the symmetries are there, are exact statements about the theory, and so they remain highly constrained. And there's a recent paper with some progress in this direction by that group. Okay, so now I'm going to go on to some work in progress, which is very much in progress, but looking at sort of asking a different kind of set of questions about this. Again, with postdoc and student at Harvard and Nima, and what are we looking at here? Okay, so we've been looking at the 4-graviton scattering amplitude, and the first thing we want to do is, and this is a standard assumption, the standard assumption is that gravity has to be very soft at very high energies. And why does gravity have to be very soft? Typical amplitudes have to be exponentially soft at high energies. This is because at high energies, you make a black hole basically with, its energy gets big enough, you make a black hole basically with probability 1, and that has a lot of entropy in it, so there are exponentially large numbers of final states, and since there are exponentially large numbers of final states, the individual cross sections where you specify all the incoming and outgoing momenta should vanish exponentially. Okay, so that's an assumption, and this would apply to the case where we take the center of mass energy to infinity while keeping the ratio of T over S, which works out to be the conformal cross ratio on the sphere, fixed. Okay, so the kind of question we're asking is what kinds of singularities? So there's lots of discussion about singularities, structure of the S matrix in momentum space, and what kinds of things could we expect for the celestial 4-point amplitude. Now, it's maybe not that hard to, maybe not so surprising, but these people have shown that the celestial 4-point amplitude can be written in a form so that there's some kinematic prefactors here, but the guts of it depend only on two things, one of which is the sum of all 4 conformal weights. It can't depend on them individually. The kinematic prefactor does, but the guts of it depends only on the sum, and the conformal cross ratio Z, which, though I haven't discussed this here, has to be real by translation invariance. Okay, so at tree level, we would expect some kind of amplitudes which would be some power of S times some power of Z, and with some coefficients APQ. And these APQ, as has been discussed by people in the amplitudes community, obey all kinds of interesting positivity constraints. Now, this thing, because it's exponentially soft, and here we're just putting this in, there can't be any divergences in this at large S. And so the only way you can get a divergence is at S equals 0. And it's easy to see that if we have an A that's going like S to the P, that would be a term in the low energy effective action, because we're looking at low energies, that will produce a pole when the conformal weight is equal to, okay, you have to put all the factors in there, but when the sum of the conformal weights is P minus 4. So the structure we expect at tree level is that these celestial amplitudes are meromorphic with poles along the only place where you can get poles is along the real negative axis. Now, in the full quantum theory, we'll also get logarithms, but if we assume that this amplitude isn't going to infinity somewhere, the only place we can get divergences again is at small s, and it's not too hard to see, which is if you have the pth power of a logarithm at small s, the simple pole becomes a pole of order p. Now in general, these logarithms appear, of course, we're constructing exclusive, we're computing exclusive amplitudes here in perturbation theory, and so there's going to be some IR divergences. It would be interesting, but we have not addressed the question of, IR finite scattering cross sections involving dress states. That would be an interesting thing to do, but we haven't done that. But one thing that you can see here is that the leading infrared divergence, the leading power of S, which will give you the leading pole, it doesn't involve the cutoff, and so the leading pole at any given place on the negative delta axis should be an infrared safe quantity characterizing the scattering amplitude. So anyway, and we also looked at some quantum field theory amplitudes, and there you can get poles piling up into cuts, and so there's a different kind of structure appearing there. So let me just now mention a few open questions. Okay, so I've thrown out some hopefully interesting facts about these celestial conformal field theories. And some of these questions have come up along the way. One is, to what extent, how much do the symmetries constrain the theory? How much freedom is left after you impose all these symmetries? There was a long, very nice paper by Gade and Minwala and the group at TIFR characterizing the most general for graviton amplitude, but not all of these would be, not all of them would be invariant under all the asymptotic symmetries. So there is more to be learned as far as implementing the asymptotic symmetries as constraints on scattering amplitudes and OPEs. Actually, OPEs was what I was asking about here. It seems that the OPEs are simpler things to work with than the scattering amplitudes. Of course, a question which maybe should go before this is, what are all the asymptotic symmetries? We thought we knew all of them 15 years ago, but then more started appearing, and we're not sure exactly how many there are, and in what way they get corrected, and to what extent they persist to the quantum theory. Now, in ordinary conformal field theory, when you know the spectrum and you know the OPEs, that fully determines the two-dimensional conformal field theory, and one might hope that something similar is true here, that characterizing all the OPEs in the spectrum characterizes a 4D quantum theory of gravity. Now, there's been a lot of work recently about crossing symmetry and bootstrap and conformal block expansions in ordinary conformal field theory, but here we're at a much more rudimentary stage. We'd like to understand if there is a conformal block expansion and whether we can match up the OPEs with the expected conformal blocks and reproduce the amplitude. Of course, there is always a conformal partial wave expansion. That was already worked out by the group at Brown, but that hasn't been yet cast into a form of a conformal block expansion, which should tell us about some notion of what a complete set of operators might be. And as I was mentioning at the end, it's interesting to understand what can be said about the analytic structure of the celestial endpoint function. And I think a really especially interesting question, which I've been focusing on, is what is the most general form of the Graviton 4-point function? As I said before, many people have been looking from different points of view and finding various things which constrain it, and perhaps we can put them all together and find the general 4-point amplitude consistent with all known symmetries, and perhaps it looks something like the expressions we get out of string theory. There's certainly been conjectures to that effect. And in conclusion, the reformulation of Minkowski, 4-dimensional Minkowski scattering amplitude as correlators on a celestial sphere is leading to some novel insights, and there's a lot of things to do and to try to understand. Thank you for listening. Laura.
So for is there any implication for amplitude in typical momentum space?
For what?
Conformal sub-zero.
Yes.
Is there any implication for amplitude in momentum space?
No, I wouldn't say that there's implication for the amplitude in momentum space, because we basically derived it from the conformal soft theorem in momentum space. So most of the way it's gone so far, Fineman diagrams in momentum space we've been, analyzing for a century, and we understand them really well. And actually, if you look at this intertwined approaches, Fineman diagrams and soft theorems, boundary conditions, uplifting ADC formulation, among these 4 different things here, it's the Fineman diagrams that we understand the best. Nobody ever argues about what momentum space Fineman diagrams are. So most of the, or how to evaluate them. So, and that is the connection between all these things has sort of, most of the flow of information has been from Fineman diagrams, translating them into these other language. And it certainly taught us a lot about, even in the BMS story, it wasn't just the BMS group. There was the Newman-Unti group. There were various other groups depending on the boundary conditions. But the Fineman diagrams, everybody agrees what a Fineman diagram is, so far we haven't learned anything new about what happens in momentum space. Yes.
Can you say, so as far as I remember, they were looking at local 4 graviton interactions, and they were asking which ones obeyed causality and one that the amplitude doesn't grow too fast. And you mentioned that there could also be bounds from asymptotic symmetries. Can you say more about that?
Well, yeah, so the asymptotic symmetries, are not, they'll relate different amplitudes, and they'll put constraints on the amplitudes, and we just saw, in fact, how they determine, in simple cases, they determine the OPEs, so there's no guarantee, and indeed it seems unlikely that all these possible different forms of the 4-graviton scattering amplitude are consistent with all these symmetries.
Do the symmetries know about the growth of the amplitude at high energy, or do they relate different growth rates?
No, I don't think so. But I'm not completely sure. I mean, usually the natural way, one of the things, the natural way to think of trees is, I think, on the celestial sphere. So if you want to think about the various soft theorems and so on, the fact that they're encoded in current algebras on this celestial sphere is is of the various ways of describing them, it seems to me the simplest. And so the idea would be that by describing things in that way, you can make more progress in finding out what the implications of those symmetries are. It's pretty non-trivial that well, let me just start there. Yeah.
So back to this issue about the convergence of these Manet transforms. One of the theories, we know that many times the true-level amplitude stages violate unitarity, but once you resum the vertical expansion in a certain way, you can restore unitarity. So
Right.
do you expect that if you take an amplitude which is well-behaved at energies, meaning unitary, then at least it's marginally convergent, or do you expect that some amplitudes, even if they're unitary, they just don't make any sense?
Well, first of all, I think the real power of this approach is for quantum gravity, where you have the full conformal symmetry, not just the global part. And there we expect strong convergence at high energy, and that strong convergence, as I noted, implies that the amplitudes are meromorphic in the plane of conformal complex plane of in the plane of complex conformal weights. Now, in ordinary quantum field theory, I'm on a little shakier ground because I'm not sure to what extent the conformal symmetry is, the full conformal symmetry is realized, or what the SL2C subgroup does for you. It should be true at large n. So you could take a gauge theory coupled to gravity and then take large n, and then at large n you have only the gauge theory correlators. So somehow large n correlators should be obey all these properties. But in general, I would say it's an exploration. But I'm more optimistic about learning something about quantum gravity, something new about quantum gravity than about quantum field theory, though the latter is also interesting. Yeah.
Doesn't that depend on your choice of the boundary condition?
Well, okay, so maybe I should have rephrased it. Yes, that is the huge problem, that there are lots of papers, I'm going to choose this boundary condition, this is asymptotic symmetry, then somebody else says I'm going to choose this boundary condition, and I have some other asymptotic symmetry group. But what those papers tend not to show is that the asymptotic symmetry group that they get, all of it acts non-trivially. So, and not only that, they also tend not to show that, I mean, all the papers, one of the reasons BMS, for example, another thing that can happen is people could put too strong of a boundary condition in. So Penrose's conformal compactification basically kills the BMS group. So so you can put too strong boundary conditions on, kill physically important symmetries, or you can put too weak ones on and have symmetries that act trivially. So the precise way of how you phrase this question mathematically and which things are important, that's what hasn't been understood, and that's why I put that as an open question. And for example, there are now a number of groups, number of papers written saying that it doesn't stop at the simplest thing are the leading and the subleading soft theorem in gauge theory and leading, subleading, and sub-subleading in gravity. But there have also been papers now that's saying that if you project out the lower angular momentum modes, that you have higher and higher soft theorems related to higher and higher asymptotic symmetries that involve projecting out of more and more angular momentum modes. And the way that you see this is, you see the naive thing is that even in the Maxwell theory, it's confusing. In the Maxwell theory, you would think that if you specify the gauge field at infinity, that's the naive thing. You specify the gauge field at infinity, and the leading term, the 1 over r piece of the gauge field at infinity, and then the equations of motion determine all the subleading terms. In fact, that's not quite true, because there's an integration constant that lives, it doesn't give you a function all on scry, but it's an integration constant that lives on the sphere. And those are like boundary modes, which are typically the kind of thing that would be associated with symmetry. And you get a new one at every order of perturbation theory. And we don't know which of those we don't know if all of those are non-trivial or not. My feeling is we've probably gotten all of it now, that it's the leading, subleading, and sub-subleading in gravity, and the leading and the subleading in gauge theory, but I'm not very sure. And there's also a lot more to understand, like in supersymmetry, we don't know what, there's things associated with scalars and with higher rank tensor fields, and yeah, so there's a lot of stuff we don't understand.
Okay, let's thank Andy again.